In our today's lecture, we're going to talk about different compounds that contain organic compounds that contain oxygen, alcohols, phenols, thiols, and ethers. So alcohol contains hydroxyl group, illustrated here and here. Phenol is different from a regular alcohol is because hydroxyl group is bound to a benzene ring instead of an alkyl chain. A thiol contains the sulfhydryl group, SH, and the ether contains the group that is oxygen between two carbon atoms. In the alcohol names, in the IUPAC system, the E of alkane is replaced with OL. So for instance, the alcohol that is derivative of methane, when one hydrogen is replaced by OH, is methanol. Ethane, ethanol. The alternative way to name is, instead of methanol, to say methyl alcohol or ethyl alcohol. So basically, you give the name of the alkyl group followed by alcohol. So let's take a look at some naming of alcohols. What are we naming this one? First, we need to identify the longest carbon chain, which will be this. This longest carbon chain contains 6 carbons, so it's going to be hexa, and it's going to be some kind of a hexanol. Now we need to figure out where OH group is placed numerically, and it's at the second carbon, so it's 2-hexanol, and it has a substituent relatively to OH group, which is going to be methyl. So at the end of the day, it's going to be 5-methyl-2-hexanol. So alcohols can be classified by the number of alkyl groups that are attached to the carbon that is bonded to the hydroxyl. If there's only one alkyl group bound to that carbon, it's the primary alcohol. If there are 2 alkyl groups bound to that carbon, it's secondary alcohol. 3 alkyl groups mean tertiary alcohol. Generally speaking, alcohols are polar because they contain polar hydroxyl groups, which bear slightly negative charge on oxygen and slightly positive charge on the hydrogen. So they technically can form hydrogen bonds with the water molecules. Hydrogen bonds are illustrated by these dotted lines here. So the only problem is that the solubility of alcohols in water decreases as the number of carbons in the alkyl chain increases. So technically speaking, both ethanol and octanol contain polar hydroxyl group, but octanol contains so many carbons that it is not soluble in water. So you can see here that only first 3 alcohols, methanol, ethanol, and propanol, are actually soluble in water. Starting from butanol, solubility drastically decreases. Now phenols are slightly soluble in water. They have a polar hydroxyl group. It can form hydrogen bonds with water. Actually, phenols can give hydrogen away, producing so-called phenoxide ions and hydronium ion. Phenols were widely used as antiseptics. The solutions of phenol in water were called a carbolic acid. Now alcohols can be dehydrated, okay, which can result in the production of alkene and water. So in this particular reaction of dehydration that occurs when there is an acidic catalyst and heat is applied, water molecule leaves the alcohol, leaving the alkene molecule with a double bond. Now let's talk about oxidation and reduction in organic chemistry. So in organic chemistry, oxidation increases the number of carbon-oxygen bonds, by either addition of oxygen or loss of hydrogen. Reactions of reduction reduce the number of bonds between carbon and oxygen atoms through the opposite processes. So for instance, when alkane gets oxidized, it can form an alcohol and vice versa. So the number of carbon-hydrogen bonds is increased. When alcohol is oxidized, it will produce aldehyde. So now you can see that number of carbon-oxygen bonds is doubled compared to the alcohol. When aldehyde is oxidized, it produces carboxylic acid. Here you can see that carbon forms 3 bonds with oxygen compared to only 2 in aldehyde. So oxidation of primary alcohols, which increases the number of bonds between carbon and oxygen, results in the production of aldehyde. Here you can see an aldehyde molecule with a typical carbonyl functional group. Further oxidation of aldehydes results in the production of carboxylic acid, where the carbon forms 3 bonds with oxygen in carboxylic functional group. Now what about secondary alcohols, where the central carbon bound to OH group is bound to 2 more alkyl groups? Oxidation of secondary alcohols results in the production of ketones. And ketones cannot be oxidized any further. Now tertiary alcohols cannot be readily oxidized, since there is no hydrogen atom bonded to the carbon that in turn carries hydroxyl group. So they can't really form a double bond or something like that. So generally speaking, tertiary alcohols are not oxidized. Now thiols are pretty interesting compounds, sulfur organic compounds. So they contain a thiol SH group. Many thiols, the majority of thiols, have very strong and very nasty odors. Spray of skunk contains a mixture of thiols, cheese, onion, garlic, oysters. As a matter of fact, methyl thiol is used to detect gas leaks. It is added to otherwise non-odorous natural gas, and when you smell a gas, as a matter of fact, you smell a thiol, not actual propane or methane. So thiols are named by adding thiol to the alkane name of the longest carbon chain, and you number the carbon chains from the end that is closer to SH group. So methane thiol, ethane thiol, to butane thiol. So here are some examples. Methane thiol is found in cheese and oysters. Propane thiol found in onion, and propene thiol is found in garlic. When thiols undergo oxidation, hydrogen atom is lost from 2 SH groups, from 2 different thiol molecules, which produces a disulfide. Basically, it's somewhat similar to ether in some case. So, as a matter of fact, the protein keratin that is found in hair is cross-linked. So, different parts of the protein are connected by disulfide bonds. And those disulfide bonds are formed by thiol groups found in amino acid cysteine. So here you can see a protein chain with thiol group sticking out and another protein chain with thiol group sticking out. And when they are oxidized, they form a disulfide bond. Disulfide bonds are extremely important for the function of biological molecules. Now, ethers contain an oxygen between 2 carbons that are alkyls or aromatic rings. Usually ethers have a bent structure like a water, and usually has a common name that consists of alkyl names of the attached groups followed by ether, like in case of this dimethyl ether. So here you have methyl propyl ether. It's a common name. Okay, so we're not going to talk about IUPAC naming of ethers. We're going to use only common names of ethers. Alkyl or aromatic groups are written in alphabetical order. So in this case, it's going to be methyl, propyl, but not the other way around, because methyl comes first alphabetically. Now let's talk about carbonyl groups. So carbonyl group, found in aldehydes and ketones, consists of a carbon-oxygen double bond, which is very, very polar, and two groups of atoms are attached to the carbon. Oxygen atom is extremely electronegative and slightly negatively charged. It has two lone pairs of electrons, and it forms a strong dipole with a carbon. The carbon is slightly positively charged, while oxygen slightly negatively charged. So in aldehyde, a carbonyl group is attached to a carbon atom and at least one hydrogen. In the ketone, a carbonyl group is attached to two alkyl groups, to two carbons. In many cases, aldehyde group in condensed structural formulas is written as CHO, where double bonds are sort of, understood. Everybody appreciates that. In a ketone, the carbonyl groups can sometimes be written as just CO, like a single in a condensed formula. So here you have CHO in aldehyde, here you have CO in a ketone. So when you name an aldehyde, you take an IUPAC name in which the alkane name is used, but the last E is replaced to Al. So common names for the first four is aldehyde. So form aldehyde, acetaldehyde, propionaldehyde, butyraldehyde. Those are common names. Those are not IUPAC names. So in IUPAC names, formaldehyde with one carbon will be methanal. Acetaldehyde will be ethanol. Propionaldehyde will be propanal, and butyraldehyde will be butanal. So let's take a look at the name of this particular aldehyde. So we need to identify the longest carbon chain, which will be this. And this carbon chain must include the CHO group. So 5 carbons, pentanal. And then we have a substituent, which is second to aldehyde group. So it's going to be 2-methyl pentanal. In naming ketones, we replace in the alkane with ONE. So with a common name, alkyl groups attached to the carbonyl groups, named alphabetically, and they followed by ketone. So propanone, dimethyl ketone, another name is acetone. Butanone, ethyl methyl ketone. 3, because it's at the third position, pentanone, diethyl ketone. Here, cyclohexanone, substituent is at the third carbon, so 3-methyl cyclohexanone. So let's name this ketone here, shall we? First, we need to identify the longest carbon chain. So it's pentanone. This is the carbon number 2, so this will be a carbon number 4. So 2-pentanone, it shows you where the ketone group is. And the methyl substituent is at the 4, so 4-methyl 2-pentanone. Aldehydes and ketones are usually soluble in water because they can form hydrogen bonds between carbonyl oxygen and hydrogens in the water molecules. When they have 4 or fewer carbons, they're very, very water soluble. When they have longer hydrocarbon chains, so they're aromatic or they have large cyclic structures that are nonpolar. These nonpolar carbon chains or cycles, they diminish the ability of ketones and aldehydes to dissolve in water and diminish the solubility effect of the polar carbonyl group. So this illustrates solubility. So basically the way to butanone and butanol, it's soluble, and then the solubility decreases from the 5 carbons and farther. They're very useful. Acetone or propanone is a solvent, very popular solvent, paint, nail polish remover. Formaldehyde is the gas, and its water solution is used to preserve various biological specimens. Now, Tollens test is used to distinguish aldehydes from ketones. Turns out that Tollens reagent, which contains silver, single positively charged, only aldehydes but not ketones are capable of reducing, aldehydes, yes, aldehydes reduce silver to metallic silver, and in the test tube it will look like a mirror. It's called the reaction of a silver mirror that results in the production of acetic acid and silver precipitating on the walls of the tube. Now, Benedict's test, or Benedict's reagent, which contains copper, allows you to determine presence of aldehydes in the solution. So Benedict's reagent allows you to specifically determine the presence of aldehydes which contain hydroxyl group adjacent to the carbonyl group. In this case, Benedict's reagent, which contains copper, it's basically copper sulfate, copper to sulfate, oxidizes hydroxypropanol to hydroxypropanoic acid, producing this brick red precipitate. This test is negative for simple aldehydes or ketones, the ones that do not contain the adjacent hydroxyl group. So here you can see Benedict's test is used to determine monosaccharides in the solution, because monosaccharides essentially have a aldehyde group at one end that has an adjacent hydroxyl to it. So blue Benedict's reagent, after the interaction with the glucose, results in the production of gluconic acid and brick red copper 1 oxide, shown here, and that's a really convenient test for the sugars. Now, aldehydes and ketones can be reduced. They can be reduced by various compounds, such as sodium borohydride or hydrogen. So after the reduction, the number of bonds between the carbon and oxygen is reduced, either via addition of hydrogen or loss of oxygen. The catalyst for this reaction can be nickel, platinum, or palladium, or other metals of the 8th group. And this is how this reaction looks like. So if you will bubble hydrogen through the propanol over the platinum catalyst, it will result in the production of 1 propanol, or primary alcohol. If we will do the same and bubble hydrogen over the nickel catalyst through the propanone or dimethyl ketone or acetone, it will result in the production of 2-propanol or secondary alcohol, isopropyl alcohol. So aldehydes form primary alcohols, ketones form secondary alcohols. This concept map shows you the classification of different compounds that belong to alcohols and ketones.